Hello, my name is Júlio and I'm the technical co-founder of Fractal. We're hard at work building the Fractal protocol, which will enable privacy-preserving radical markets for data to help keep the web open and free for everyone. And joining us today is Martin Pompéry. He's the co-founder and co-chairman of the SINE Foundation. Xena is a non-profit organization specialized in cryptography and in economics. You can think of it as a think and do tank that is focused on making secure multi-party computation more than just a theoretical foundation, but to actually develop its practical uses. And we're working together on building a smart cookie. And that is a next generation cookie with a cryptographic and self-sovereign twist. And we'll dive deeper into this in a little bit, but first let's get to know Martin a little bit better. Martin, can you tell us a bit about your past work and what brought you to Xena?
Well, first of all, thank you for having me.
It's a pleasure, always.
It's a really great pleasure to see you person in that COVID situation, right? It's literally one of the first.
Oh yeah, it's the first time we're meeting in person,
yes,
isn't
exactly.
it? Yeah, I just realized. You're right.
Yes, yeah, it's just video calls all day, right? So regarding my background, I'm a software engineer by trade. I came to cryptography by a very stupid question, if you want, by a customer at a company that I was working quite a year ago. And that was, we would also like to send more user identifiable information. Back in the days, I was working for a company that was collecting data for advertisement purposes, meaning imagine you are an app publisher and you want to target your users in a certain way with advertisements. So that a publisher was then sending information to the company, and we were collecting it in a way that you can really pinpoint an individual when you are doing, let's say, advertisements at Facebook. And so there was this bank asking, we would also like to, I'm quoting them, but more or less liking to send us the amount of money that a specific person would have on our account. I mean, not literally, but in a figurative sense. So they can, for instance, schedule advertisements based on, let's say, credits, depending on your bank account, which, by generally speaking, might make sense from a bank's perspective. But of course, this was prohibited by the terms of the service by that company. So we did never accept that type of data and would never have done so. But the question was interesting to me in the sense of that maybe there's a way how to do that, but in a way that doesn't evade the privacy of the person, so that we don't need to necessarily have the bank account, or maybe there's some way to that. And so we started looking into that a lot more, and that basically got me into the rabbit hole, which is cryptography. I mean, if you look that up, you obviously pretty early get on the question of cryptography, and so we got to research that a lot. Funnily enough, when I was studying computer science back in the days, it was very much math heavy, and back in the days it was a diploma. So it was literally undergraduate mathematics studies plus computer science plus some other topic, and so I was very, very early on familiar with the notation, what was going on there, and it was just fun to see what cryptography enables. It's literally, it blew my mind once I started to get into that, and it never really stopped blowing my mind when I read recent publications. So what's going on there is, I think, spectacular. And when I saw the breakthrough papers from, let's say, in the period of 2015 to 2017, where the effort and the algorithmic complexity went down so much, that was just so mind-blowing to see that within 2 years, I know, 3 orders of magnitudes of effort were reduced just by algorithmics. I don't know a single area in computer science that has these breakthroughs in such a way.
Yeah, no, that is impressive.
It's super impressive. I mean, my background originally is database systems, and there we are happy. I don't know if about 5x, 10x is like mind-boggling.
Yeah, and very linear programs.
Exactly. I mean, this is just amazing and unheard of. And yeah, there was this paper, and yeah, by the way, there's another paper based on that, and we get a factor of 5 faster, and we think, oh, well, it's nice, well, just by some algorithms, and so that took me into the space, basically. So yeah.
So it was almost kind of like, well, if this technology is available to us, then we should be using it more than we are now.
Yeah, exactly. Yeah, exactly. And then you see, wait, actually, there are only very few initiatives, very few companies actually leveraging that technology to its full extent, right? Obviously, in the blockchain space at large, there's lots and lots of crazy and great stuff going on, right? Within Fractal, of course. and many other projects, especially in the zero knowledge space, etc. We have seen this Cambridge or this explosion of research, right? This is absolutely unheard of, and you can also see that in the academic output that once blockchain really took off, you can also see that there's more funding in the cryptography space, and there's much more done and made practical, and we try to adhere to the tradition. If you want, trying to make cryptography available to more people in a more or less direct way, and but not just making cryptography available for the sake of cryptography, but for the sake of sovereignty, right? So we really, as SINE, we really focus on the sovereignty of companies and individuals alike. We want to make this technology available so they become more sovereign in the current status of the internet and the service landscape, and we try to productize that. And so joining with Fractal was like crazily great for us, because we exactly align on these values, right? We really want to put more sovereignty in the hands of the people, and so do you. So.
And I guess it's in this context that Xena was founded. In this, you realize that there's a lot that secured multi-party computation and cryptography technology in general could be used today in ways that it is not, and you're trying to make sure that that is a thing. Can you tell us a bit more about Xena itself? Like how was it founded, and what are you guys focused on right now, and like what can we expect in the future? Like what are the goals of Xena?
Yeah. So being SINE is a bunch of people right now, and some of them working full time, some of them working part time. So in total we have 40 members. So this is a non-profit. This is more like from a legal perspective, it's the same structure as a club, and we have this structure of a club, meaning we have this. Yeah, we have really a huge number of people who are great experts in diverse fields, cryptography and non-cryptography. And we have the cryptography experts and economics experts. So the way I like to describe SINE is really like we are a T-shaped organization, meaning we have these broad depths and expertise with people from many different areas, as I mentioned. And we have this special expertise in economics and cryptography, and try to combine that to make that usable. Speaking of how it was founded, it was founded by Ora Stenzel, myself, and a lot of other people. In total, we were 14 people founding SINE initially, so technically they are all the founders. I'm just one of them. I just happen to be starting this initiative a little bit earlier than the others, but essentially this is really a members-driven thing. We are more than 40 members now. We are active in two spheres, if you want, very much in the business sphere, which is together with the World Business Council, we are defining standards. And also in the second step, cryptographic means how to exchange emissions data between the different parties. And we have the same situation here. The parties want to keep sovereignty over the data, but still want to make it actionable. For instance, they want to understand where do my emissions come from in my very complex supply chain. This involves sovereignty of many different stakeholders that we are trying to get all combined properly in a process that involves standardization and technology, very much similar to what we are doing with Fractal, of course. And the other space is getting more sovereignty in the hands of the, so to say, of the normal people, meaning non-business people, just the normal people, especially also in the healthcare domain, etc., partially also advertisement, as we will be talking about, I guess, in a few seconds. So that's what we are talking about. We have these two different areas, just normal private people, businesses, standardization and cryptography. That's the main areas that we're working on.
Got it. Because the smart cookie really is just one way, as we'll talk about, or one application of secure multi-party computation. Exactly. There's a lot more that can be done with it. Yeah. Maybe we start with a quick overview first for our audience on what secure multi-party computation is. And I guess you could say that it is a method that allows multiple parties, and that is multiple people or computer programs or whatever it may be, to agree on the computation of a certain result based on data that each party is providing, but in a way that no other party can have access to this data. And this has two very important properties. One of them is that it's privacy preserving. Because while everybody has access to the shared result that was computed, no party can glean on any other party's data. And second, this is verifiable because every party can be sure that even though they don't have access to the initial data from the other parties, that the result of the computation is correct. And I'll illustrate this with a classic, which is Yao's millionaire problem, where you have, I mean, it's not really an important problem, but it's an illustrative one, where you have 3 millionaires at a dinner party, and they're trying to figure out which one is richest. But they just met each other, so they don't know each other, they don't trust each other, they don't want to reveal their net worth. So how could they figure this out? Well, an approach would be, this is a bit naive, but just to illustrate, the first millionaire could take a calculator and write down her net worth. And then she would add a random number to this net worth before passing the calculator to the second millionaire. The second millionaire then adds their net worth to this and passes the calculator to the third, who does the same and returns it to the first. So now in the calculator, we've got 3 net worths added plus a random number that the first chose. So the first millionaire subtracts the random number that she chose before, and she can divide the result by 3 in order to get to the average net worth. And by sharing that average net worth, then every millionaire that is on the table, whose net worth is inferior to this average, they will know they are not the richest. And this is a very basic example, but secure multi-party computation can be used for a lot more. You can imagine it as a mechanism to run a verifiable election, where every party, every participant, every voter can be mathematically sure of the outcome of this election without needing to know any of the other votes or how the other people voted at all. So you can see how promising this is. Martin, would you add anything to this explanation? Well, I'm sure, because you're the expert, but like anything that you would say here?
I like the explanation very much. It's absolutely on point and correct. There's just one more line, tiny little thing that I would like to add here, which is you don't necessarily even have to share the results with everyone. You even have control over that. And I think we might be talking about that briefly later, but I think this gives the whole approach even more, how can I say, more interesting use cases.
Got it.
Because you have the full life cycle control, so to say.
I'm looking forward to going into detail
Exactly.
when we're talking a little bit.
Exactly.
All right, so this is the first part. Let's do a quick overview of what smart cookies are as well, before we take a peek under the hood. So, as you know, the ad tech market is still scrambling to understand how it will survive the death of the third-party cookie. And while the industry fights around like whose solution is best for this, we thought like, hey, how about we provide a free and practical alternative to this problem to allow websites to keep operating as they do, but with much lower technical and regulatory requirements on this data, as we will see. And in a way that they verifiably respect user consent, user privacy, and their choice. Here's an example. If a user has the Fractal wallet installed, then website owners can create and update the smart cookie that lives inside the Fractal wallet to essentially build their first-party data and to make user-specific decisions. This would allow them, like cookies normally do, to deliver targeted advertising, realize higher prices for their inventory, customize the content of their websites, and even support schemes such as, for example, 3 free articles a week. And they can do all of this without users having to log in, without having to store any specific user data on their site, and without users even sharing any data that belongs to them. So users retain full control over their data. They can always reject the website's requests to read from the smart cookie, for example, or even create it in the first place. They can just delete this cookie and then it's all gone because all the data stays with the user. And that is why the smart cookie fits so well into the Fractal protocol mission, because it aligns user consent and privacy with ad tech functionality. It allows us to sidestep this trade-off between like data usability and data privacy, because we can do both at the same time. And then that's what the smart cookie is about. So now that we've gone through this introduction, let's take a little bit, let's look into the details a little bit. So still, Martin, without getting too technical, what role does secure multi-party computation play in delivering this smart cookie?
First of all, it delivers the privacy part, obviously, right? So meaning the input from the advertiser or from the website that is using the smart cookie technology, as well as the input from the user, is all encrypted all the time. And as I just mentioned, also the output can stay encrypted and stay encrypted locally at the device of the user. So this is first of all enabled by the secure multi-party computation technology in general. Second of all, as a website publisher, for instance, you can be sure that whenever the program is running, meaning the smart cookie is actually executing, so to say, locally on the device of a user of a Fractal protocol, they can be sure that actually the protocol is kept, meaning that whatever you want to happen with a smart cookie locally, the engine ensures that this is actually going to happen, meaning that you cannot make up data, so to say. Speaking of the 3 articles a week, there's obviously a certain incentive to try to mess with that, so to say, and you could completely work around that, meaning you would not have to count how many articles has a certain user actually seen as a website publisher. You can just make sure that you count correctly, so to say, store the data in the smart cookie, and you're done. So it's actually very much simpler, I would say, compared to what they have to do right now.
Yeah, it's a lot more.
Right. You push all of the responsibility that you would normally have to do all by yourself down to the Fractal wallet, and you don't have to care about the correctness. Like this is so to say the whole idea here, right? This that you can push out, so to say, problems that you would normally solve by yourself, have it done by the Fractal wallet, and don't have to care about the correctness. But it's ensured that it's actually correct what's happening there. It's like a dream come true, I would say, as a publisher.
Yeah, so as a user, it is entirely up to you whether or not you agree with this interaction, but you can't really lie during this interaction, right? You cannot change the data on your end and the website be none the wiser. This is something that offers that guarantee as well.
Exactly. And you also, obviously, as you mentioned, always have this parachute, so to say, right? If you're not okay with what's happening there, or you don't trust things suddenly for whatever reason, you can always just delete the data, right? And it's gone.
Got it.
Right? Without any trace. And I think this really to me, this would always mean sovereignty, right? You stay in ultimate control. You have the ability to exit what's going on there, and you can always start from new, etc., etc., etc. And you always ask for consent before something happens.
Of course.
But it's not just a consent like a rocket that you shoot away and then you hope that it works. But it's right. This will never lose your system, right? Or sorry, the data will never leave your system necessarily. You have control over that. I think this is amazing.
Yeah, and you don't even have to store, like as a website owner, as a publisher, for example, you don't even have to create user accounts to store that information on your end, to think about like, what does this mean for my regulatory compliance requirements in terms of like what data am I storing, how am I associating with the user, how am I storing this data? This just kind of disappears and stops being a concern as well.
Exactly. Or you can work together with third-party providers, right? Maybe you have, maybe you as a publisher work with an agency, and they help you design the smart cookie. Like you can safely outsource this, right? You don't have to get into GDPR trouble at all, right? So it's not just the publisher that gains a lot of flexibility, so to say, and the user sovereignty. It's also how you can cooperate with different parties, right?
And speaking of cooperation, actually, something that we haven't really mentioned super obviously yet is that we're talking about 2 parties. We're talking about a website and a user. But this is multi-party computation. More than these 2 parties can be involved in this process. And that means, for example, that different websites could cooperate by using the same smart cookie. And this could be used, for example, in the context of click attribution in advertising. Could you speak a bit to like how this technology enables that?
Yeah, so first of all, the technology would enable that even though each publisher, let's say you're visiting a news website and you're visiting later let's say Tesla.com because you saw an advertisement and you're suddenly interested in an electric car. So let's imagine you offer as Tesla a certain discount on your car if you're coming through the channel. For instance, I don't know, free upgrade for leather shares or something like this in your car. So how would that work? So in general, each website would have its own smart cookie to start with, right? This is obviously a flip side of the sovereignty part. So each website has its own smart cookie. But then Tesla might ask you, would you like to have an upgrade if you are coming from a certain website? And as a user, you would probably say, yeah, sure, why not? And then after this consent has been given by a Fractal user, the data of the both smart cookies will then be computed to see whether there's a discount option available or not. Again, this would not entail sending any data to, let's say, the news website or to Tesla for whatever reason. All of that computation would happen locally, but it would involve the consent of all parties, meaning Tesla would have to consent to that, the news publisher, and you as a user. So it's an active protocol, so to say. And if one party, or if at least one party sticks to the protocol, which obviously, or in most cases, hopefully the Fractal user will be, for instance, then the data stays secure all the time for all the different parties. So that's one thing that we haven't talked about so much, and I guess we'll talk about later. But the security guarantee, which I think is really important to mention here, is that exactly, it's super critical. And second of all, really just one party is enough to secure all the data, right? And if it's a Fractal user who follows the protocol, everything stays secure, and there's no way around that.
Got it. Yeah. This is this cooperation is for me is making a really big difference here, because it's kind of what enables us to promise that the smart cookie will make sure that websites do retain their functionality, because it's not just about the relationship between the website and the user. The web is a more intricate web than just that, and making sure that folks can still interoperate is something that I think is really, really important. All right, so I think we've cleared the most, the more basic concepts around this and how it all works together. So maybe you could share a little bit more about like the theoretical foundations that the secure multi-party computation engine that you guys are building. Like, what do they look like? What is this built on top of? Could you share a little bit?
Yeah, sure. So that's a big question. Let me first start with the theoretical foundations, if you want. It really goes back to what you mentioned with the Yao's millionaires problem, right? That was 1986, and the famous question, how can we compute that? And Yao basically came up with so-called garbled circuits. And garbled circuits is one of the two major streams in secure multi-party computation that you can do. We picked this stream because there was a paper published in 2017 by Wang, Ranucci, and Katz, commonly just called WRK17, because the name of the paper and the author is just so long.
Not very good at branding.
Exactly. The branding is not perfect, but the paper is great. That's for sure. So they essentially published a paper that was really a breakthrough for the so-called active security, secure multi-party computation. So active security means that the highest security level you can think of. So it's literally two mutually distrusting parties. They can do effectively anything that you can think of, divert from the protocol, try to guess certain bits, etc., etc. This is all being handled by the protocol. And before that, the protocols that were practical, and this practical here really meaning in terms of performance numbers, were not with that security level. So they literally dropped in many cases the performance by, sorry, not drop, but they increased the performance by 1 order of magnitude, meaning
which is what you were talking about.
Exactly. This was just a breakthrough paper, to my best understanding. That was really a breakthrough, and the protocol or parts of it have been reused in other protocols. It's a heavily cited paper, and they not only just published one paper, and they first published one paper for the two-party case, so it's just you and me computing, and then they published the paper, which is essentially just an extension of the original paper, showing that you can also use this technology for multiple parties. So they scaled this up literally. So they made two-party secure multi-party computation under active security practical, and then they showed you can also scale this to multiple parties, and that was literally like a breakthrough to me.
And that's also super recent, like you said. That's 3 years old now.
Exactly. It's 3 years old now, and there have even been more, as usually the case. There have been even more improvements to certain details of the protocol, and just recently there was a paper published which seems like we can even improve the performance of the protocol even more, right? This has been published last week, so it has to be seen. But essentially, this is exactly what I was mentioning, right? We have this explosion in terms of performance and research activity in the space, like we saw a few years ago with zero knowledge proof, and we see the same here with secure multi-party computation. So that's going on there. This is the foundation. We also factor in some other papers to accelerate certain other specific parts of the protocol called OT, but essentially the major work that we base our work on is a peer research paper from 2017 and onwards, exactly. So that's the underlying theoretical foundation. In terms of technology, what the engine does is Garbled circuits really means circuits in the sense of computer hardware, meaning when you I don't know how many of the people who are watching this video have even had that, but essentially when you have a computer these days, it's made up of logical gates, right? You have an AND gate, you have an XOR gate, etc., etc. So this is a very literally the bits and pieces of a computer, how a computer is actually computing. Right?
I think most folks don't have no idea, but this audience might be different.
Exactly. So essentially, it's like the atomics that make up a modern computer, so to say, are called gates, and a gate is computing a certain function. And so what the engine does is, the way how you can conceptualize the engine is literally like a computer that can be programmed. So whenever you execute a program, you're executing the program at this gate level, so it's this atomic computational unit. That's what the engine does, and it's securing that this computation is taking place properly, as we had it already, and also that the input, especially that is being fed into this computer, this very special computer, is being kept secure at all times. So it's literally like a virtual CPU. If people are familiar with the term, it's like a virtual CPU, like a virtual smartphone that you put in a browser, in the Fractal wallet, and you put into the servers of, for instance, a news publisher. And whenever the engine gets active and starts computing something, it's like these two or more systems are forming a virtual CPU, which is then computing the function that is supposed to be taking place. Meaning that when they're actually working with the smart cookie, it's like a virtual CPU synthesis for the sake of a millisecond, and then this vanishes again. That's what's happening. That's what's happening there on the technical foundation level.
I think virtual CPU is a good analogy for what this is doing for the engine that you guys are building. And can you explain a little bit more into like how it preserves the privacy of those inputs and how it guarantees verifiability to the different parties involved?
Yeah, great question. That very much refers to what you described initially with the Yars millionaire problem, right? Where you have a calculator and you add a certain number and then you pass the calculator on. That's very similar to how the protocol works. So the security is enabled in multiple steps, if you want, and at multiple locations. But the way you can think of is that even before the data enters this virtual CPU, it's already encrypted with a very big key. And then this key changes over time as the data passes through the program. And it's not only is the key changing, if you want, but for the situations where operations are being done which could potentially leak information away, you again do the shuffling and authentication of the data. That's the one thing you do. The other thing you do is, this is usually called masking. Like you're obfuscating the data that is coming into the system in a way that it is absolutely impossible to discriminate the input data or the data that you get from the actual input data. This is like statistically made impossible. And the other security guarantee that the protocol gives you is that whenever, and that's what I mentioned with active security, whenever somebody tries to change a bit somewhere, for instance, let's say you outsource the computation and somebody's changing a bit here and there. This exactly, just a single bit, right? This is being detected. So whenever you go through the program, and for instance, in the end, you want to decrypt what actually the result is, there you would then encounter, wait, something doesn't add up here, literally.
So you might not know where exactly the problem comes from, but you do know that you're not supposed to trust that at that point.
Exactly. Exactly. So you can stop the protocol, and this the stopping is usually a huge problem, which sounds very trivial to do, right? But stopping is a problem in the sense of that if you can make this other party stop at a certain point in time, you can start to infer where potentially this one bit has been changed and been detected. And by that you can maybe also infer something about the input data. And even that which is extremely unlikely to happen, even that is being covered for by the protocol. That's why it's called actively secure. Right? So like literally, and the security is being proven in a mathematical way. This is not engineered security, this is security in a mathematical way. with clearly
cryptographic security.
Exactly, it's cryptographic security that is being proven and peer reviewed. That's the difference. Also, for instance, if I may say, that's the difference between, for instance, so-called secure enclave technology that you can get with modern CPUs that also smartphones these days have. The problem here really is that with these secure enclaves is that you really have to trust the hardware vendor. You have to trust them that this is actually working.
You have no guarantees.
Exactly. Of course, they have great engineers and they do whatever they can, but eventually you, as a customer of that CPU, you have to trust the claims of the vendor. And here with our software, it's the obvious. It's really the opposite situation. We have open source software. It's a peer-reviewed protocol. We will be showing additional results in terms of proving the security of what we are implementing. This will be delivering eventually, etc., etc. So we have full transparency over the software. You have transparency over the algorithms. Algorithms are peer-reviewed. This is obviously a completely different situation to secure enclaves.
Yeah, of course.
And that's also why we went down the software road, which and that's the other thing that I want to mention, which is I think really crucial here, is that first of all, speaking of standards, etc., the engine will be open source, free to use for everyone. Meaning everyone literally can make use of the technology, be it a publisher, be it a commercial product, be it Fractal, using it for their wallet, no question, right? Everybody can use it, and we really want it to be used by everyone because we think it's so foundational, and everybody should be using it. You
don't want to close source something that you really want to see out in the world, right?
Exactly. And so what does it mean? Well, what does it mean from a user's perspective? We want to make secure multi-party computation literally universally applicable, right? And how can you do that? We think only through software, because when it's just a piece of software, it means we can also run it, for instance, through WebAssembler in a very fast way in a browser. Meaning wherever you go as a user, as a Fractal user, and you're visiting a website, essentially you can make use of the technology, right? And we think this is only possible through software. If we were relying on special features of a hardware device or whatever, obviously this would never be a ubiquitous technology.
Yeah, of course, and it's also, as you said before, like more verifiable. It's easier for anybody to inspect that the thing is doing the right thing, because it is not a closed source piece of hardware that is integrated in some chipset, and that would become. I mean, obviously, verifiability is a good goal in itself, but even if you were to say, well, like, why would this manufacturer kind of like, lie within their secure enclave? Well, if you have a vertically integrated business and you're also making chipsets, like some folks that I know, then that could not naturally be an issue, because you have an incentive to lie. You do have an incentive to turn computation into your advantage. Yeah. And this is something that by doing this in software, with software that is inspectable, with software that is open source, that anybody can improve and anybody can verify, this naturally brings up, is a lot more trustworthy for the environment.
Exactly, and there's one more thing which I really like about software. Well, if you do something wrong, I mean, you can always deliver an update, right? So it's very easy to retrospectively fix something.
Not so much on hardware, yeah.
Exactly, and we have seen that, which is very sad, in the so-called trusted enclave space, that there have been multiple breaches, like breaches that were so fundamental that literally the system was broken. That is being documented properly enough, and of course, I mean, as I said, software, like, people make mistakes with software, and we are doing our best to make everything we can. That is really the most secure multi-party computation that has been written so far. But it's software; it will improve over time. So, not trying to make false promises here. Although I can definitely say that we're trying everything we can to make this as secure as possible. And if you do something wrong, we can always deliver an update. That's what I'm trying to say.
Nobody has to trust your word, because again, it is open source.
Exactly. Yeah. And even if we did something wrong, still, the data is encrypted all the time, right? So we should really screw up majorly if data was lost by the execution of our protocol. Because, by the way, we are going to run this through the Fractal wallet. I mean, the data will stay locally to the user's device, right? So the data is leaking to a third party is really, really, really low. Even if we screw it up, right? It's still extremely. It's I wouldn't call it impossible, but it's extremely really low likely that this is actually going to happen. So,
got it.
So much for that.
You were telling me before about how stopping the protocol is one of the hard parts that are involved in implementing this correctly. What other maybe non-intuitive, like tricky parts are there to building this out?
That's a great question. So one of the tricky things really is to program the engine. As I mentioned, it's at the so-called gate level, at the atomic level, if you want, of programming. There's literally almost no more low-level way to program a computer than this.
In terms of developer experience,
exactly, it's not so good, and this applies sadly to most of the secure multi-party computations that exist on Earth. Right, it's really a niche technology, if you want. Also, I mean, starting from the terminology, right? What is active security? No one knows. Right? I mean, what would you guess what active security is? I would think of active security like something as bumpers, right? Mm-hmm. What is active security? I don't know. I mean, as a lay person, I would have absolutely no idea. So it starts with the terminology. And it goes down to the programmability. Right? These engines are hard to compile sometimes. I mean, they are projects which only deal with how can you compile as many secure multi-party computation engines as possible so that you can do your work as a researcher. So it literally starts by that very simple thing as building an engine, understanding the terminology, and then making use of it, meaning being able to implement something that is meaningful on top of it without becoming a secure multi-party computation expert. This hasn't really been done from a developer experience. If you are a well-trained person in cryptography and you are a very specialized computer scientist, that might be doable for you. But if you are not such a person, then you would have a really hard time to understand what's going on there. And so that's what we definitely want to change with the smart cookies. So together with you, meaning you as Fractal, and your colleagues, we really want to sit down and find a programming language that is proper for the use case, which is secure by design, meaning where you can really reason about what's going on there, what are the security guarantees, privacy guarantees that you can get out of that computation, and we will be making this available in a way that also just the normal developer, so to say, normal experts without cryptographic background can make actually use of it, etc., etc. I mean, obviously, smart cookie is a technology for the web, so we should make it available for the normal web developers, so to say, and not for the cryptography experts. That's what we want to do.
So it's part of bringing this product into the world to make sure that, you build abstraction layers on top of it to make the product usable for everyone. Exactly. It is not about just what the product can do, but how we build the product in a way that it can be easily used by anyone that already is a web developer, and they don't have to learn the logic of how gates actually operate and have only used a very limited set of operations, but instead they have a fully powerful programming language on top of that to allow them to implement custom functionality.
Exactly. That's exactly the thing.
Yeah, I'm very much looking forward to that part as well, because that is really going to be what the kicker is that enables widespread adoption of this. And again, it goes hand in hand with everything else that we're doing in that direction, right? Like this being open source, this being something that is made usable because there is an implementation of the technology that is available, but not just all of this. It is made usable because people can easily use that implementation of the technology by writing in this programming language that exists on top of it.
Exactly.
Perfect. Martin, other than the smart cookie, and I gave the voting example before, and I suppose that it is still a really tough problem to tell who is the richest at the table. Are there other applications of secure multi-party computation that you're excited about?
Yeah, I'm really excited about anything that's related to health. I mean, we are in advanced talks with a big hospital to use health data from the so-called second health market to detect rare diseases. So what is the second healthcare market? It's, for instance, let's say all of these fitness wristbands where certain data about your body is collected, for instance, like heart rate, etc. And you can really greatly infer a lot about that. And if you start to infer, let's say, heart rate and use of websites, etc., a good friend of mine has shown that you, for instance, can automatically detect depression. Like if you are able to correlate behavior over time, and you see when behavior changes, you can really see that there are certain patterns, for instance, with depression, that you can detect really early on when somebody has a depression or is developing a depression.
Maybe even before they themselves know.
Exactly. In many cases, they have seen in the studies. I mean, they did literally a large-scale study with more than 300,000 users a couple of years ago, where they could show that there were really a lot of people having depressions, like which then later were also diagnosed with depression. I think this is an amazing thing to do for everyone involved. And doing this in a way that it doesn't evade the privacy. I mean, obviously this is a very delicate topic.
It's extremely sensitive.
Exactly, it's a super sensitive thing. And the way they carried that out was as a research project, so they had the proper setting, made sure that the data is secured, etc., etc. But that was done on a really, really large amount of money and effort that they had to put into that. And we think that with our technology and by cooperating with you, we can really enable that for way, way more people, and also in a very much more low-key way, so to say, right?
I think so too, and I'm very excited about that.
Yeah.
Martin, thank you very much for your time today. I think we should do this again in a few weeks and give folks an update on the project and how it's going.
Yep.
This is something that we're looking forward to having roughly at the end of Q1, and I think that at that point we'll really be able to see this like working in the real world. I'm very excited about this, so thank you for coming on board and like helping folks understand a little bit more about this shared project.
Thank you.
It was a pleasure.
Thank you, it was a pleasure as well.
Cheers.
Thank you, ciao.